Hello everyone. Welcome to today's Bangalore Theory Seminar Series. Today we are very excited to have Vijay Bhattiprolu as our speaker, as our guest speaker. So Vijay is an assistant professor at University of Waterloo. Prior that, he was postdoc at Institute of Advanced Study at Princeton University, and he is advised by Venkatesh Guruswamy in uh, Carnegie Mellon University. So today is we'll talk on his recent exciting work, which is titled as Inapproximability of the Sparsest Vector in Real Subspace. So let's welcome Vijay.
Thanks for the kind introduction and thanks for hosting me. You've been very charitable. Okay. So today we'll talk about approximability, that is NP hardness of approximation of finding the sparsest vector, sparsest non-zero vector in a real subspace. And this is joint work with Uyung Lee at University of Michigan. Okay, so the formal statement of the problem is the following. This is an optimization problem. Given a subspace V over n-dimensional reals, n-dimensional Euclidean space. Sorry? Sure. Yeah. Or kernel, either one is okay. Yeah. You're given a subspace encoded via a basis of the reals. And want to approximate the minimum sparsity of a non-zero vector in the subspace. Okay. So minimum over x in V minus the origin of the sparsity of x. Okay, so by this notation, I refer to the number of non-zero vectors in X. Okay. And let's develop a little bit more notation. Let's call this this zero norm of this subspace V, even though it's not a norm. Okay. And the following is our main theorem that today's talk is about. So under randomized reductions, we have NP hardness. So unless NP is in BPP, for all constants C greater than 1, no polytime algorithm can distinguish between the following two cases. The case where there exists a sparse vector in the subspace. Yeah, that's the number of non-zero entries in the vector X. Yeah. Okay, so also known as the sparsity of the vector. Okay. Yeah, the minimizer may not be unique. Yeah. Yeah. So for example, in Reed-Solomon code, you can have many. Yeah. Okay. In the S case, there exists X and V minus 0 such that the sparsity. Another question? Yeah. Yeah, I think that's correct. Yeah, good point. Yeah. Okay. The no case for all x, for all non-zero x, the sparsity is at least c times d. Okay. Let's start with some remarks on this theorem before we get to motivation. Sorry? Yeah, okay, good. So I should be careful with the quantifiers here. For all c greater than 1, there exists some d, some parameter d, such that you cannot distinguish between these two. And d will be polynomial in the dimension n. Okay. Okay. So this in particular implies you cannot approximate this quantity within any constant factor. Okay, unless NP is in BPP. Okay. So some remarks. I believe the previous best gap known for this problem was 1 plus 1 over poly n. Okay. Pretty much exact NP hardness was known, and not much was known beyond that to my knowledge. Okay. But also over finite fields and over the integers, analogous results to this were known. Okay. So previously known over finite fields, FQ, and integers. See. So what do I mean by that? So over finite fields, it's the same problem. You minimize x in a subspace that's non-zero. Of the non-zero, the number of non-zero entries in X. Okay, V is a subspace of FQ to the n. And the analogous problem people have studied intensively over integers was you let S be the integer span of a set of vectors, summation alpha I Vi. Oh, different markers, sorry. Yeah, no problem. Yeah. I was about to ask actually, I forgot. Polynomial in n. Yeah. So there's a wide gap. Yeah. Okay, so the analogous problem that has been studied over the integers is you look at a lattice. What is a lattice? It's the set of integer linear combinations of a set of vectors. Okay, so summation alpha I Vi such that alpha is in z to the n. And you study the minimum length of a non-zero vector in this lattice. So x belongs to S minus 0, x L2 norm or LP norm or any number of other norms. Okay, so this first problem has another name. This is the minimum distance of a code. And the second problem has another name. It's called the shortest vector problem. And for both of these problems, constant factor approximations have been ruled out under similar assumptions. NP not in BPP. Okay. In fact, for minimum distance, it's P not equal to NP. Okay. Okay, good. So I want to highlight some features of the proof. So the proof. Sorry? Is hard, but to my knowledge, actually, before this result, it was not known. And the reason is the sparsity version on lattice is equivalent to this problem where V has integer entries. I mean, the basis has integer entries. Exactly. Yeah. Good question. Okay, so one nice feature of this is the proof is quite simple and it entirely avoids the PCP theorem. Okay, the PCP theorem, if you haven't heard of this, is this cornerstone result in hardness of approximation. And it's quite rare that you can avoid the use of this theorem in a hardness result. Okay. And furthermore, the reduction is even more simple. I highlight this because I think in cryptography, it's useful to be able to easily generate hard instances. The shortest vector problem is a foundational problem in lattice-based cryptography. And I don't know much about this, but I'm hoping some cryptographer will see the merit in an easy reduction for generating hard instances of the shortest vector problem. Okay. Okay. So in fact, in the yes case, we have an additional property that there exists a 0, 1 vector that has this sparsity. Okay, and because of this, we get SVP hardness as immediate corollary. Okay. When you have a 0, 1 vector, the L2 norm, the L0 norm, the LP norm are all equal. Because of this, it takes a minute to observe why this is the case, but as an immediate corollary, we recover hardness of the shortest vector problem. Yeah. Exactly. And it gives L2 norm, LP norm, all P. Yeah, exactly. Yeah. It has a 0, 1 vector. Yeah. Okay. And so final remark, this is a standard trick in the area by tensoring. As you map the subspace V to V tensor T, where T is a large constant, or even polylog n. Gap can be boosted to 2 to the log 1 minus epsilon n, assuming NP is not contained in randomized quasi-poly time. Okay. Good. Okay, so now I'm ready to motivate this result a little bit. You'll have to forgive me for going quite quickly through the motivation because I'm eager to tell you the proof. I'll be able to fit most of the proof in this talk, hopefully. Okay, so the first motivation I have for studying this result, for studying this problem, is inapproximability is well established for discrete optimization problems. But far from it for complete problems. Okay. Or for continuous problems, I'm sorry. In fact, whenever your continuous problem gives good value to a sparse vector, we don't know good hardness techniques. Okay, so this is one of my major motivations for studying this. Okay. Before sort of going further into this difficulty, I just want to describe the PCP theorem and how it's typically used to you a little bit if you've never seen it before. Okay. So it's a brief overview of discrete methodology.
like this is sort of intriguing, like it's 0, 1, right? So if I write the following like optimization problem, which is just minimizing the, let's say, the L2 norm of x subject to x being in the subspace. This does, I mean, the yes condition does, so I'm certainly missing something. Because in that case, it's the objective is just L2 norm convex.
Yeah.
Minimizing it to the constraint that x lies in B, which is actually a convex.
-0. That's what makes it non-convex. Yeah. Yeah, it's an annoying detail. Yeah. 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 Good question. Yeah, so okay. Yeah, so brief overview of hardness for discrete problems. It generally all starts with the PCP theorem, which informally states it is hard to find x in some discrete set, sigma to the n. So think of sigma as constant. For example, you can think of sigma is equal to 0, 1 if you want. Okay. It is hard to find x in a discrete set, even approximately, maximum number that simultaneously satisfies the maximum possible number of local constraints. Okay, that is, you have a series of constraints on this vector x, each involving constantly many variables. Okay, and your goal is to find an x that satisfies as many possible constraints. I mean, as many constraints as possible. Okay, English is my second language, so, at least according to Canada. Yeah, yeah. Okay, so yes, this is what the theorem says. And this turns out to be extremely versatile for proving hardness of other problems. Okay, and then the keywords here are this. This is a feature. The fact that every constraint involves a few variables, and you get this hardness. And the fact that this alphabet size is also constant. Both of these aspects are really, really good features. Okay, and I'll say a little bit about why. Okay. Versatility of local constraints. Okay. So as an example, let's pick two problems. Okay, so one problem that we know is hard, and another problem that we want to show is hard. Both are going to be local in nature. I want to show you how the locality of the starting hard problem helps you prove hardness for this destination problem. So let's pick local quadratic equations. I can pick any number of examples here, but let's pick local quadratic equations. So that is, you have a system of quadratic equations, q1 of x equals b1, dot qm of x equals bm. And each of these quadratic polynomials involves only constantly many variables. Okay, so we start with the assumption that this problem is hard. Okay, and you want to show, let's say, 3 variable linear equations over f2 to the n is hard. Okay, and then this local quadratic equations also, let's say, over f2 to the n. Okay, which you can identify with 0, 1 to the n if you want. Okay. So the typical paradigm here, this local gadget reduction paradigm, is that you replace each variable in your original instance by a cloud of variables. So a cloud of new variables, cloud of x1, cloud of x2, and so on. Okay, and whenever you have some constraint here involving some constant subset of the variables, let's say qi of x, right, you're going to replace that constraint by a cloud of new linear constraints. Okay, so you're going to have some cloud of qi, but the only power you're allowed here is to add 3 variable linear equation constraints. Okay, so you're going to replace this one quadratic constraint by an enormous number of 3 variable linear equation constraints. Okay, the reason you're going to need an enormous number is that you cannot simulate quadratics with linear without massive, blow up. You need exponential blow up to simulate quadratic with linear. Now that's where the fact that these are local comes into play. This massive blow up of the constraint is not harmful now because this is still constant size, even though it's exponential in that constant. Okay. Good. So that's why. So that's why this has become such a versatile framework, and probably 90% of hardness results follow this schematic. Okay. Now one problem with this for continuous problems is that these local gadget reductions, right? Yeah. Exactly. Yeah, exactly. So it's like n times or m times exponential of a constant. That's the new size. Yeah, exactly. So you have this. Yeah. Okay. Now, on the other hand, the problem with this is if you try to look at some problem over r to the n instead of f2 to the n, or even z to the n instead of f2 to the n, you run into this problem where there exist, for any gadget reduction, there exist these vectors that are non-zero on a very small subset and zero everywhere else. Okay? And these vectors, if they have high value on your optimization problem, they're problematic because it's very hard to take these vectors and decode a good assignment to quadratic equations. Okay? So most local gadget reductions, without some geometric information about the set of quadratics, will have sparse vectors in them. Okay, so these reductions generally break. Okay, and then they break actually on a variety of problems. Okay, so let's write this here. Local reductions don't work for many problems. Okay, so I'll just give you a little bit of a list. So sparsest vector over even f2 to the n, z to the n, r to the n, all these problems it breaks. Okay, maximize polynomials over convex sets. Those reductions break. Graph expansion problems, and so on. So this list goes on. Okay, so this sparse vector issue is a problematic issue. Okay, so this is one of my main motivations for studying hardness of this problem. It is perhaps one of the lowest hanging representatives that I could study to circumvent this bottleneck. Okay. Okay. A little bit more motivation before we move on. So my second motivation comes from analytic variants of sparsity. Okay. We can define an analogous problem to the sparsest vector in a subspace, right? That looks like the following. We minimize over all non-zero vectors x in a real subspace. The ratio of the LP and L2 norms for any p greater than 2. Okay. So this quantity here ends up behaving like an analytic variation of sparsity. Okay. It's more robust now. So you can take a vector that was sparse earlier and noise it a little bit. And this notion will stay the same. However, this L0 notion can change massively. Okay. So I really care about showing hardness for this problem. And then my main reason for that comes from this result with Uyung Lee and Asaf Naor, I think it was 21, that hardness of this problem for every p greater than 2 will imply a host of new continuous optimization hardness results. Okay, so it will imply hardness of maximize x transpose AX, where X belongs to a convex set C. Okay, so when you want to maximize a quadratic polynomial over a convex set, for some choices of convex set, this problem is easy. For some choices, it's hard. And for a while, I've been working on what the characterization is of when it goes easy, when it's easy and when it's hard. And over time, we identified a candidate geometric invariant of this convex set C that should tell you, roughly speaking, when it's easy and when it's hard. Okay, and that geometric invariant is called the type 2 value of this convex set. I will not go into this now because I want to show you some details of the proof. But loosely speaking, just think of this as it's a measure of how quickly a random walk escapes the convex set. Okay, so if you can prove hardness of this problem, automatically by some embedding reasons, you get a host of new hardness results. That is, maximizing quadratics over a convex set is difficult whenever random walks quickly escape the convex set. Okay, whenever the type 2 value of C is large. Yeah, I'm being very informal here, forgive me. And on the flip side, the converse of this theorem with some bells and whistles is true. So we also showed that if T2 of C is bounded by a constant, and you have some separation oracle, okay, this is a little bit of a weird, bizarre assumption. I will be the first to admit that, but we are unable to remove this assumption so far. So if you have these two things, then you have an algorithm for this problem. Okay. So in other words, if you can show NP hardness of this problem, you approach a characterization of when quadratic maximization over a convex set is possible and when it isn't. Okay, this is a very expressive class of problems. If you want to get a sense for why, well, linear function maximization over convex sets is all of convex optimization. So this is a generalization of that. Okay, captures many easy and many hard things. Okay. Yeah. So whatever hardness you get here will transport over here. So if you get almost polynomial, you'll get that here. And if you get constant here, you'll get almost polynomial by tensoring again. Okay, cool. Okay, so that's one motivation. And another one is if you do the same thing, minimum x and v, non-zero v, now we study what's called the 2 to 4 norm, the ratio of the 2 and 4 norms. This problem plays an important role in quantum information and in small set expansion. Okay, so hardness of this will imply something about classical complexity of the quantum separability problem. It's some problem where you want to tell if a state is close to entangled or not. Okay, and this is some long-standing problem in quantum information theory. So if you can get hardness of this, you'll get hardness of this, some classical hardness of this. Okay, and the final connection I want to highlight is that you could view these types of results as an intermediate step towards small set expansion. The reason is the following. So if you minimize over x epsilon close in, let's say, the L2 norm to the subspace. Yeah, I don't need this now. X not equal to 0 of the sparsity. this captures small set expansion of a graph. Okay, by taking the subspace V to be the top eigenspace of the graph. Okay, this is another important problem in complexity theory, and so yeah, proving this result is hard. Proving this problem is hard will be an intermediate step towards that, hopefully. Okay, right. So that completes my motivation. Sorry for the extended motivation. No, it's on the way to that. So 2 to 4 is harder than what I've done so far. Yeah. So these analytic versions are even harder. But I will say the reduction, it's already led to progress on this problem for one value of P. I can't do any more than that at the moment. But the hope is, to keep building and then get here eventually. I think this is the hardest. So this is slightly easier goal. This is the hardest goal, and L0 is the even easier. Yeah. Exactly. Yeah, that's somehow a fundamental change. Yeah. But you maintain the property that the denominator norm is greater than the numerator norm. Otherwise, it doesn't behave as a sparsity notion. It'll instead prioritize dense vectors. Okay. Great. Okay. So with that, let's get to overview of hardness results over finite fields and over the integers. And we can finally get to the reduction. Okay. Okay. Okay, so if you're wondering where do all these hardness results come from, one common ingredient in most hardness results is error correcting codes. Okay. Now we have ways of circumventing usage of these objects, but the old proof of the PCP theorem made extensive use of error correcting codes. Okay. And I'll say a little bit about that now to just show you, why it's so powerful. You can get an idea of where you can get constant gap out of nothing just by seeing this. It'll be very quick. Okay. So the error correcting code, I'll abbreviate this to ECC from now on. Okay. Is a map C from F2 to the little n to a larger dimensional space, F2 to the capital N. You can also change the field. Okay, this notion you can define for any field. An error correcting code of distance d, let's say. Okay, so it's a map mapping vectors from a smaller space to vectors of a bigger space, such that for any two non-equal vectors, their distance after the mapping is big. Okay, distance C of x, C of y is at least t for all x not equal to y. Okay, and here by distance over finite fields, we mean the number of entries on which they disagree. So the Hamming distance. Okay, and ECC is linear, so it's called a linear error correcting code if C is a linear map. Okay, and this is by now an result, there exist codes with amazing parameters. Okay, there exist maps C, linear maps, mapping f2 to the little n to f2 to the theta n. Okay, so just a constant blow up in the dimension such that the distance of the code is linear in the number of entries. Okay, so you take two vectors that can disagree in one coordinate, and now just by mapping them to a constant factor higher dimension, they disagree now in constant fraction of all coordinates. Okay, so it has this distance amplification property, which is extremely useful for hardness. The reason is that all the time you have these good assignments and you have bad assignments, and you want to distinguish them significantly. So you want to encode good assignments and bad assignments in a way that they're very far apart, so that simple tests can distinguish them. Okay, so this is at a high level, that's why it works. But today you'll see some concrete examples of why it works, or some concrete details about why it works. Okay, so one final comment: if the code is linear, if code is linear, distance of C is equal to the sparsity of the sparsest non-zero vector. Okay, the reason is you can replace C of x by 0 here. Okay, so C of 0, so the distance to 0 is equal to the smallest distance between any 2 points because of linearity. Okay, good. So in the PCP theorem, the first step in the original algebraic proof of the PCP theorem, the first step gets hardness, constant factor hardness for quadratic equations. Okay, and it works as follows. I'll be able to show it to you in a minute. So you start from hardness, exact NP hardness. Of checking if q1 of x equals b1 dot qm of x equals bm is satisfiable. Okay, so it's NP hard to check that there exists an x, let's say an f2 to the n. Okay, that satisfies all these equations, or that there exists no x simultaneously satisfying all those equations. Okay, so this is NP hard. Start with this assumption. And now consider new system, okay, given by this error correcting code. So you start with an instance of this original hard problem, and we are going to define a new system, code times q1 of x till qm of x must equal code times the vector b. Okay, so yeah, think of C as a matrix, right? It has these entries in its rows. So the first row of this product is Ci q1, I mean C11 q1 of x, C12 q2 of x, and so on. You sum them up, you get some new quadratic that must equal to that summation of the bi's. Okay, and you get a system of new quadratics like this. Okay, one thing I want you to notice is that if you started with local quadratic equations, that's completely lost now because you summed up the equations. Okay, however, what this does gain is instant constant factor gap. Okay, just from this coding property. Okay, and let's see why. So in the yes case, all equations are still satisfied. Right? So in the yes case, there exists an x satisfying all these equations. Plug in that x here. This vector will be b. So c times b must be equal to c times b. Right? In the no case, for all vectors x, one of these q's is not equal to the b. So this vector in the no case, for any choice of x, this vector is not equal to b. And we said the property of the code is that any two non-equal vectors are unequal on constant fraction of the coordinates. So constant factor of these new quadratic equations will now be incorrect. Okay. Okay, instant hardness, right? Yeah. Yeah, that's correct. Yeah. Okay. So then we did note how, okay, now these are no longer local, so they're not that useful for proving hardness of new things. And I just wanted to make the offhanded comment that the PCB theorem does significant work on top of this step to now make these quadratics local. Okay. And the key idea in doing this is the Reed-Muller code. So another error correcting code comes into play in order to make these quadratics local. Okay. But let's not go into this because, again, the goal for today is different, a bit orthogonal to this. Okay. So it's not making the code local. Okay, it's a good question. So yeah, so okay, there exist sparse matrices C that have the same coding property. Okay, but there's a subtle reason that if you try to apply those, it won't work. This constant factor gap we got won't work. I'll explain that to you offline. Yeah. Okay, so sparsifying C is not sufficient. There exists sparse Cs, and that's kind of it's in the right direction. It's related to locally testable versus locally decodable. These are different things. It's related to that. Okay. 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 So we have what, 20 minutes left? Is that? Yeah. Okay. Perfect. All right. So I got to go a little quicker. Okay. So I did mention that over finite fields and over integers, these hardness results, this hardness result is known, right? But I also mentioned to you that those are also problems where you have this local reduction bottleneck, right? So how do those results work? I'll give you a very brief schematic. By now, it's a large area of research with many papers. And then the schematic that came about in this area, it's very successful, is the following. You start with PCP theorem. So you get, let's say, hardness of local quadratics. Okay, each one involving few variables. And then you do a local gadget reduction to get hardness of sparsest vector in an affine subspace. Okay, so you must be thinking, what's going on? I said local gadget reductions don't work. So there's this subtle but serious issue, which is it's quite straightforward to prove hardness of these affine versions of the problem, non-homogeneous versions of the problem. Okay, I'll give you a very bird's eye view of why this, like, allowing to shift the subspace can be beneficial. So let V be equal to span of E1 through En over 2. So the first half elementary vectors. Okay. So this has a ton of sparse vectors in it. In fact, it has all the elementary vectors, right? But then now if you just look at all ones plus V, the bottom N over 2 coordinates will always be all ones. Okay. So now every vector in this new subspace has at least constant sparsity. Okay. So it has linear bits of information. You can use that to decode assignments to quadratic equations. This is a very brief sketch of why this is a lot easier to deal with. Okay, so because it's a lot easier to deal with, they first get here, right? Okay. And let's also say that these ideas were pioneered by Aitai and Michiancio, and then refined in several other papers that I can't do justice to. Okay. And then this is where the magic happens. This is where the more global transformation happens. We mentioned local transformations don't work. So now you do this, you use this global coding gadget. I won't show you these gadgets today, but to prove this result, I'll show you the gadget that we use. Okay, you then use a global coding gadget to get hardness of sparsest vector in subspace. This time not affine. Okay. In a similar way to how we got hardness out of nowhere from here, you do it there too. Okay. So you can use these global coding gadgets to simulate an affine sparsity problem with just a sparsity in subspace problem. Okay. Okay. Okay, so the first major ingredient in our reduction, I'll have to give you intuition before I give you the reduction. Okay, so I'm first going to give you a toy ingredient. So the first major ingredient in our reduction is testing if a matrix is rank 1 via the usage of tensor codes. Okay, this is inspired by a simplified proof of finite field hardness due to Austin and Court in 2010, I believe. Okay. So the idea is the following. It's a two-part idea. Okay. Rank 1 test can be used to simulate quadratic constraints using linear constraints. Okay, that is what do I mean by this? If you have a test that given a matrix, okay, a test that fits into the problem you're studying, that given a matrix, it gives the matrix good value only when it's rank 1 and otherwise doesn't. If you have such a test, you can use that to simulate quadratic equations with linear constraints, right? Why? So any quadratic can be written as Qi inner product XX transpose, where Qi is a matrix. Okay, any quadratic Qi of X can be just written in this inner product form between two matrices, the outer product matrix and this Qi, right? So then if you add the constraint Qi inner product M equals Bi and test if M is rank 1, right? Then this allows you to simulate quadratic constraints because either M is rank 2 or higher, and you will get low value on this objective for different reasons, or M is rank 1, and when M is rank 1, this is exactly simulating the quadratic. Okay, so this is the idea. So if you can have such a magical test, then you can simulate quadratic equations. Okay, so we have a linear problem, right? X must be in a linear subspace, and we want to minimize the sparsity. So our powers are twofold. Sparsity checker, linear constraints. These are our powers. And using that, we need to simulate difficult things like quadratic equations. Okay, so the idea is you can do something like this, right? And moreover, yeah, not clear at the moment. This is this is also a hairy issue that, yeah, hopefully it will become more clear to you later in the talk, but I may not get to it. Yeah, I'm being quite imprecise here. Yeah. So moreover, rank 1 testing can be done. Okay. Or in fact, let me just directly state to you, because I don't want to be imprecise there, let me directly state to you the lemma that they prove, okay, that we then generalize to the reals, and it becomes the core, one of the core components of our reduction. Okay, good. So the lemma is the following. Let's see a code in a finite field. Of distance d. Okay, so you have some good code. And consider any matrix that belongs in C tensor C. Okay, if you've never seen this tensor product of two vector spaces, it's an operation that takes a subspace over Rn, and it, oh sorry, not in this case, not Rn, it's Fq to the n cross n. Yeah, it takes a subspace over some vector space, and it's now a set of matrices, okay, n cross n, and it's defined as follows. Erase this. So C tensor C is equal to the span of y transpose such that y belongs to C. Okay. Equivalently, it's also equal to the set of matrices y such that rows, both the rows and columns of y. Okay. I should specify something else, is a symmetric tensor product. It's a set of symmetric matrices, I'm sorry. Okay. So it's also equal to the set of matrices whose rows and columns all belong to the subspace C. Okay, these are two equivalent definitions of this tensor product. Okay. So here's a really nice fact. If your code has distance d, then its tensor product has distance d squared. Oh, yeah. Okay, so let's prove this because we're going to adapt this proof in a moment. Okay, so consider any y inside C tensor C that's non-zero. Okay. So you have this matrix y. Because it's non-zero, some row of y must be non-zero. Correct? Some entry must be non-zero, so that row must be non-zero as a vector. Okay. But that row belongs to C. So then by the coding property of C, that row has d non-zero entries. Right? But then we also know that these columns now are non-zero because they have at least one non-zero entry. But each of them must have d non-zero entries. So you get the sparsity of y is at least d squared. Okay. Good. Okay, so now this lemma is going to refine this idea. Okay, so consider any matrix in this. Okay, there are two observations. Minimum sparsity objects in C tensor C must be rank 1. Okay, and this is true in a robust way. That is, if you're rank 2 or higher, you will have a lot more non-zero entries. Okay, so moreover, if rank of y is at least 2, the sparsity of y is at least 1 plus 1 over q d square. Okay, so this is the lemma they prove. Okay, and you can see, vaguely speaking, I haven't interfaced things exactly, but you can see vaguely speaking why this is a type of product test using a sparsity checker and linear constraints. This is a set of linear constraints. This is a sparsity checker. With these two powers, we're kind of testing if something is rank 2 or rank 1. Okay, this first bullet point has a caveat, and we'll go over that later. Okay, the caveat is that, yeah, if you take a minimum sparsity vector and you look at y transpose, it has d square sparsity. But there exist guys that are worse. And that's a problem that we have to address. It's a serious problem. Okay, but that later. Okay. Okay, so the first thing I want you to notice is, unfortunately, this is the case in Austin and Court's proof. This gives you your gap, but it gets worse with Q. So as you increase the field size to super constant, you no longer have constant gap. Okay, so this is a problem that we had to address. And the way we addressed it is by saying, okay, we're not going to succeed for all codes. But if we ask more of the starting code C, we can then prove a good version of this lemma. Okay, so we prove the following. So consider a code over the reals. Of distance d, that is the this notion of distance. Okay. I don't know why I'm putting fancy C everywhere when I did regular C here. Okay. And assume you have the following overlap property. Okay. For all y1, y2 in C that are linearly independent. Okay, so y1 and y2 are linearly independent of each other. Their supports cannot overlap too much. Okay. So more formally, when we take the union of supports of y1 and y2, the size is at least alpha d for some constant alpha greater than 1. Okay, so yeah, I mean, whatever alpha you put here is the alpha you get here. Okay, so we said, okay, start with the code and impose this additional property upon it. Okay, and we prove actually that random codes satisfy this property. Okay, this additional property. If you have this, now you have constant factor gap. Well, I'll prove this lemma to you in the same way we proved this lemma. Okay, it's extremely simple. So start with some y. Okay, and so start with some non-zero y in this code. Okay, if its rank is 2, there are 2 non-zero rows at least in y, right? Okay, if there are 2 non-zero rows, this overlap property such that between those 2 rows, you have at least alpha d distinct positions where they're non-zero. So you'll have positions that look like this. Okay, so you'll have at least alpha d disjoint positions. So that, in other words, you'll have at least alpha d disjoint columns that are non-zero, right? And then because of that, each of those columns has d non-zero entries. And so now you have sparsity at least alpha d squared. Okay. Good. Okay, so we have 5 minutes left. I'll have to skip a little bit. Okay. I'll just say one line about, so now the difficulty has been pushed to obtaining a C with all these properties. Okay, So we use chaining and what's called Littlewood-Offord theory. To prove kernel of R, where R is random plus minus one matrix of appropriate dimensions, satisfies all these properties. The distance property plus the overlap property with alpha equals 2 minus epsilon. Okay. Good. Okay, so since we don't have too much time, I won't be able to show you the final proof of the reductions, completeness, and soundness, which is very simple. It's one page. But what I will do is I'll present the reduction to you. Okay, and we'll end there. Okay. Okay, so there is this final serious issue that we need to address. Okay, so you can try to take this lemma that we have and suggest a reduction. Okay, that so let's try to do it. So reduce from quadratic equations over 0, 1, let's say, to affine sparsest vector. We actually want to reduce to sparsest vector, but I'm going to show you a reduction that doesn't work, and it suffices. Yeah, it's going to be affine or sparsest, it still doesn't work. Okay, so let's try that using this product test. Let's try to do it. Okay, so the reduction is your subspace is defined as follows. So you're given an instance of quadratic equations, q1 of x equals b1 till qm of x equals bm. And you define a subspace as y in Rn cross n such that y is equal to cx c transpose for x in R little n cross little n. So C is some code that maps little n dimensions to capital N dimensions. Okay. You'll have y transpose equals y. You'll add this symmetric. Y belongs to C tensor C. Well, this constraint is redundant because of this. Okay. And then for all I, you want to simulate the quadratics on the x. Okay. So qi inner product x equals bi. Okay. The intended assignment here is that this capital X matrix is XX transpose, right? Where X is the assignment to these quadratic equations. The intended assignment to capital Y is the encoding. Y is equal to C of X transpose. Okay. So the idea is that either X and Y are both rank 1 and you simulate these quadratic equations, right? And so if there is no solution to this system, there is no rank 1 solution to this system, right? Or X is not rank 1, X is rank 2 or higher. That means this Y is rank 2 or higher. And if this Y is rank 2 or higher, this quantity will punish you. Okay. So great, the soundness actually works. Okay, we get soundness of alpha d square for this reduction. What doesn't work is the completeness. Okay, so in the yes case, you have no guarantee that this object has good sparsity, right? This could be a minimum distance code word, or it could be larger distance code word, larger sparsity. That's the problem. Okay, So to fix this, we introduced the idea of quotienting, which again was in this homogenization literature all over the place. Again, Michiancio and others have used it. So we bring that idea as well to the table and combine it to get a better reduction. Okay, so the final reduction is the following. So instead of having y be c x c transpose, we're going to allow y to be anything in this tensor code, and we're going to project it down to this x. Okay, this is where quotienting comes in. So in other words, is instead of encoding little x by c of x, we are now going to encode little x by a subspace, an entire subspace, with the guarantee that that subspace will contain a small sparsity element inside it. Okay, so the final reduction is this. Okay, so the intended assignment here is y is equal to yy transpose, where T of y, this projection down of y, so little y is any element in that subspace that encodes little x. So its projection down must be equal to this little x. Okay, x is equal to xx transpose, and z is equal to 1. This is the intended canonical assignment for the completeness case. Okay, in the soundness case, you have to prove that you can't misbehave. Okay, and believe me, the proof is half a page. Okay, the property we need for this reduction to work, we need some property from this operator t, and I'll state that to you. And it's the natural property. Yeah, I will mention. Okay, yeah, good. Yeah, this is. Yeah, it's a very good question, and it's also, yeah, let's take that offline. Yeah, I'll be able to quickly explain it, but it'll take a couple minutes. Yeah, right. Yeah. Okay, so I'll mention what this k is in a moment, and k will be roughly, you should think of it as d times 1 plus epsilon. No, t is going to be part of a coding gadget. So let me just state that. Okay. It's funny that the faculty says that, but the students are quiet. No. Yeah. Okay, in that case, I can actually show you the full proof. Maybe it'll just be 5 more minutes. Is that right? Yeah. Please feel free to walk outside without the social embarrassment if. Okay. Yeah. Actually, there was this. I was in Lassi Babai's graph isomorphism talk in CMU, and it was supposed to be a 2-hour talk. He went 4.5 hours. But
That's what I was giving it. We're done and like
yeah. Yeah, and there was this Egon Balash, who was 93 years old at the time, was in the audience. So like 100 people started in the audience, and by the end, 7 people were left. I was one of those 7 only because he was there. I was like, I'm not leaving before he leaves. I didn't understand anything, but I was there. Yeah. Okay, so where were we? We were. So I stated to you the reduction. Good. Coding gadget. So we require 2 operators. require R in R to the H cross capital N and T in R to the little n cross capital N. So T projects capital N dimensions down to little n dimensions. So you can think of T as this way. Such that kernel of R has distance d. Kernel of R has overlap property with alpha equals, let's say, 2 minus epsilon. This 2 minus epsilon is not important. You could have 1 plus epsilon here and it'll be fine. Okay. And finally, for every assignment little x we want to encode, there exists a sparse representative in its subspace. Okay. So for all little x in 0, 1 to the little n, there exists y in 0, 1 to the capital N. By the way, Ruta, this is what allows us to say 0, 1 vector in the completeness case, in the for the shortest vector stuff. Okay, so there exists a 0, 1 vector y with sparsity of y at most, or we can even say equal here, 1 plus epsilon times d. Okay, so nearly minimal sparsity representative is there in this subspace. Okay, so why should you expect this? Oh sorry, there I didn't finish it. Yeah, such that the projection of y is equal to x. Okay, this is, you should think of this as the quotienting step. That is, we are encoding an assignment little x, not by an encoding, we are encoding it by an entire subspace. Okay. So why should we expect something like this? Okay, the idea is the following. Kernel of R has distance d. Okay, when h is equal to roughly 2 times 1 minus epsilon times d times log capital N base little d. Okay, there's this sharp phase transition that happens. Okay, when the number of rows of this matrix R is precisely this, then the kernel of R has roughly this distance. Okay, this very tight phase transition happens. So in other words, it has no vectors of sparsity d minus 1. Yeah. When h is roughly this. So h is the number of rows of this matrix R. Okay, but so it has no vectors of sparsity d minus 1, but has exponentially many vectors in even 0, 1 to the capital N of sparsity 1 plus epsilon times d. Okay, so if you, that's what I mean by the sharp phase transition. So with these number of rows, you suddenly avoid all d-sparse vectors in your kernel, but the number of 1 plus epsilon times d sparse vectors that are in are exponentially many. Okay, so this sharp phase transition happens, and that's useful for us. The reason it's useful is that all these 0, 1 vectors, there are so many of them, exponentially many of them, that if you take T to be a random 0, 1 projection matrix, right, just a random 0, 1 matrix, right, from a sufficiently high dimension to a sufficiently low dimension, T will map any sufficiently large set. T times S will cover the hypercube in little n dimensions, so long as S is a sufficiently large set. Okay, S is exponentially large. It's this set of vectors. So under this random projection to a low enough dimensional space, entire hypercube will be covered. Okay, this is related to the fact that if you project a hypercube in little n dimensions down to n over 10 dimensional random subspace, it'll be the entire sphere. It covers everything. So yeah, it's not technically a projection, it's a 0-1 random matrix. Yeah, I use the word projection, but technically it's a linear. Yeah. Okay, so this is the case, and you can prove this with like chaining, union bound, all this business. You can prove this. Okay, so this is the object. So as long as you have these three properties that I wrote down here, we proved that random matrices have these properties, but the deterministic construction of this will de-randomize our hardness. So if you have these three properties, that reduction works. Okay. It is related to that phenomenon, but not the same. Yeah. JL is more about polynomially many vectors. This is more about exponentially many, but it's related. Yeah. In the sense that the random projection of a vector has very predictable behavior. JL uses that fact. Okay, good. So maybe let me do the completeness and soundness of this reduction, and we can end there. Sorry for taking you guys over time. Okay. Okay, maybe I should use a different marker. Okay. So if there exists X satisfying Q1 of X equals B1 dot Q M of X equals Bm, take any Y in 0, 1 to the N with Y0 equals 1 plus epsilon D such that Ty equals X, that particular X. Okay, such a Y exists by this property 3. For any X, there is some sparse representative in its subspace. Okay, so take such a Y and take the obvious choices. So this capital Y matrix is Y transpose. Capital X matrix is X transpose. And then Z is equal to 1. Oh, yeah. So by the way, I forgot to. Yeah. So this is why earlier I said affine sparsest vector, because earlier I had just BIs. We need only homogeneous constraints for it to be a subspace. Right? We're only allowed homogeneous constraints. So we have to introduce this additional homogeneity parameter Z just so that we have homogeneous constraints. Okay, this parameter is an annoyance because an adversary could try to set it to 0 and do some cheating. Okay, so this is something that we have to control in the reduction. It's a serious issue. It's actually a serious issue in the homogenization framework. That whole framework was developed to handle just Z equals 0. Okay. Yeah, and okay, so that's all I needed to say for that. So in the intention for Z is 1. Okay, but an adversary could set it to other things, and we'll have to control that. Okay, so take all these choices. Of course, XX transpose inner product QI is just QI of X, so it satisfies all these equations, right? Of course, this is satisfied, right? Because, yeah, exactly, by design, because we took Ty to be equal to X. So we have Ty T transpose equals Ty transpose, right, equals x transpose. Okay. So we satisfy all the conditions. And finally, y belongs to the tensor code because, yeah, okay, so y also belongs to C. Okay, but we assumed here, okay, yeah, here I missed something. Okay. Yeah, so we satisfy all the conditions. Good. Hopefully, no questions about the completeness. But by the way, in this hardness business, the completeness map most often gives you intuition for what's going on. Okay, because this is what's in tension. And then in the soundness case, you want to say that you are close to the intended assignment. Okay, so let's do soundness. Okay, so in the completeness case, we said if there exists a solution to the system of equations, then there exists a solution to the system of linear equalities that has low sparsity. Now in the soundness case, well, let's remark that the sparsity of y is at most 1 plus epsilon square p square. Okay, good. Because we took it to be y transpose, and then we had this assumption, right? Okay. So in the soundness case, we're going to show that if you have a sparse enough matrix satisfying all these equations, then you can design a solution to the quadratic system. Okay, so let's do that. So if rank of y is at least 2, then by this rank 1 testing lemma, we're already done. Okay, it already has constant fraction more sparsity than this. Okay, so here we use the fact that y lives in C tensor C. Okay, sorry, my tablet fell asleep. Yeah, yeah, exactly. Yeah, so in order to be sparse, it must be that y is rank 1. Okay, if there's a sparse assignment to this set of equations, it must be that it's rank 1. So let's consider that case. Okay, then x is equal to x transpose for some x not equal to 0, right? If y is a symmetric matrix, it's rank 1. It must be of the form little y transpose. And then x is simply equal to t y transpose t transpose. So there's some little x such that x is of this form, right? Okay. Z is equal to summation xii divided by k, which in this case is equal divided by, let's say, d times 1 plus epsilon. That's what I put here, right? Which in this case is summation xi square divided by d times 1 plus epsilon. But because this is a non-zero vector, this is strictly greater than 0. Right? So this is controlling the cheatingness of the homogeneity parameter, that constraint. So that's what this is for. What is the intuition? Well, so the one additional thing I can add here is that if Z is 0, the trace of this matrix is 0. Okay, so if a symmetric matrix has trace 0, it must be rank 2 or higher. That's what it's kind of doing for you. So it's encouraging you to set it to be non-zero. Okay, good. Okay, so we have this, but qi inner product xx transpose is equal to z times bi for all I, right? Because it satisfies all those conditions, right? So in other words, x over square root z is solution to system q1 of x equals p1 dot qm of x equals pm. So, which in the no case cannot exist. Such a solution cannot exist. There is one final detail that I hid from you, which is we need the fact that in the no case of this quadratic system, there doesn't exist an assignment over the reals, not just 0, 1. Right? We are starting with some NP hardness fact, right? So we started with NP hardness of Boolean quadratic equations. You can take NP hardness of Boolean quadratic equations and make sure in the no case there isn't even a real assignment that satisfies all the quadratic equations. You can do this simply by adding xi square equals 1. Just add all of these constraints to the system. In the yes case, you preserve xi square equals xi. Yeah. Yes case, you preserve all of them, and in the no case, nothing remains now because there is no Boolean assignment, right? Good. So that's it. That's the proof. Yeah. Okay. Yeah. So open problems. One major one is de-randomized construction of this. So de-randomization of shortest vector problem is it's a long-standing pursuit. So if you can do that, that would be great. Another large line of questioning is this analytic sparsity notions. So that's wide open. Finally, improving the gap from almost polynomial to polynomial for shortest vector problem. That's another long-standing pursuit. But I also feel like these ideas could help there too. Marginally, but somewhere. Yeah, gets you somewhere in that direction. Yeah. Okay, thanks so much. Yeah, sorry for going way over time. Yeah.
In the completeness, I see that you get a Boolean from a Boolean to
Yeah.
a Boolean.
Yeah.
For the reverse, you don't.
Yeah, okay. So just imagine that we added to this quadratic system the constraints that. Yeah. So imagine we added that. Yeah. Then you'll get it. Yeah. So okay, good. So like this reduction will work, but it will get hardness of a much simpler problem to get hardness for, which is affine sparsest vector, because this is now an affine subspace. Yeah, it seems like a minor detail, but this is the whole homogenization thing. Just going from the non-homogeneous problem to the homogeneous problem is difficult. Yeah. Somehow non-homogeneous problems, PCP itself directly works. Yeah. Thanks, everyone. Is it off now? Yeah, it's off. Oh, wow. Thank you. Okay. I like how things are done in India.
Disappeared.
Yeah. Oh, thanks so much. Yeah. I really appreciate it.
Already.
So I uploaded it to archive. I submitted it to stock. So hopefully no hitches there. Thanks very much. Yeah. I hope to get these analytic versions in the coming years.
I have heard of 2 for Pravesh.
Yeah. He's another person who's very into that.
And inside.
Oh yeah, Madhur is right. Oh, you work with Madhur?
No, I don't work
Ah,
with
okay.
him.
Yeah. Oh yeah, he's given a talk here, right?
Yeah, and he was at FST.
Uh-huh. Should I raise the board?
I don't know.
Yeah, I'll do this.
Say anything. You don't have to, I guess.
Yeah.
There are people who do it.
Uh,
Yeah, I could have helped. It's like so. You were saying this. I mean, you have some hints for me to make things work with global constraints.
Right. So one of the key freedoms we had here was the ability to impose that this matrix belongs in this tensor subspace. C tensor C. Right? That we saw that's majorly powerful. Right? You cannot do this if you have a constraint satisfaction problem. You can't just add these non-local linear constraints. Right? Imposing that something belongs in a code, it's a non-local linear constraint. Right? And we use that in a major way. Right? So this is what I mean. So if you have these hard global constraints, an example of a hard global constraint is linear equations. Then it's powerful. So similarly, in packing covering, you have these hard global constraints. And so one idea is like
For general code
exactly
instead of LTCs.
yeah, exactly. So one question I would ask you is like, can you use your hard constraints to simulate a tensor type object?
Interestingly, they're still recording. Good.
Okay. Yeah.
I don't know what will they do with this.
Yeah. Oh, is there a question as well?
No questions. I think they're still recording. I'll just stop. I don't know. I'll just tell him that recording is still going.
Oh, okay. I also have a